You know how sometimes kids ask the most difficult questions? If a 4-year-old asked you why do things exist, you'd probably struggle to give them a decent answer, because we don't really know.
If we peel away the layers of complexity from humans, to cells, to molecules, to atoms, to subatomic particles, we reach the standard model of particle physics, which is our best description so far of the fundamental machinery of the universe.
But it doesn't really answer why anything exists, but it does describe what exists and how it behaves, and that's what we'll be discovering in this video. Although it's probably not actually suitable for 4-year-olds, but for the rest of us, this is a crash course in the fundamental rules of particle physics, and it'll help set the context for future news when people claim to have evidence beyond the standard model of particle physics. You know, it's good to first of all understand what the standard model is. So that's what this video is for. We know the standard model isn't complete. There's lots of unresolved mysteries, which I'll be taking a look at the end of the video.
Particle physics is one of the main branches of fundamental physics. I've briefly covered it before in the map of physics and in the map of quantum physics. But here we're going to dig deeper and I'm going to tell you all the basics of the fundamental particles of the standard model, which I've summarised in this map, which, like all my others, is available for free digitally and for money as a physical poster. Links in the description. So here are all the fundamental particles we've discovered so far. This set is what everything in the universe is made of. There are a few distinctions to point out. These are called the fermions, and these are the bosons. Fermions make up the physical matter in the universe, and the bosons mediate how those matter particles interact with each other, and so are also known as force carriers or exchange particles. But technically, the thing that sets them apart is a specific quantity called spin. The fermions all have a spin of a half, and the bosons have got a spin of 1 or 0 for the Higgs boson. You can see these values in the chart here.
Spin in quantum mechanics is a form of angular momentum, which in general is some kind of rotating motion. But spin specifically exists within elementary particles and is also known as intrinsic angular momentum. But spin is a bit of a confusing name because it's not the same as classical spin, like spinning a basketball. There's no classical analogue for spin, so I've actually got no idea how to draw a picture of quantum spin. So this is the best I can do, but this is just an analogy.
In quantum mechanics, every particle has a wave function, and the spin of a particle tells us how the wave function behaves under rotation in 3D space. So when we rotate the spin 1 particle, we see face 1, then 2, then face 1 again. So for a spin 1 particle, the wave function looks the same after 1 full rotation. But for a spin half particle, you need 2 full rotations. So as you rotate it, you see face 1, then face 2, then face 3, then face 2, then back to 1 again. So the wave function looks the same only after 2 full rotations.
Hopefully that gives you a decent picture of spin. But it's a complex topic which I won't really be able to do justice in the time frame of this video. But how it works isn't the important thing for us for this video. The important things are the consequences of these different kinds of spin. And there's 2 things you need to know about. The first is that spin has to be conserved. It's one of the conservation laws of particle physics. Basically, there are a bunch of rules about how particles can interact with each other. These are known as the conservation laws of particle physics. And they say that there are certain quantities, like spin, that you can't create or destroy in a particle interaction. The same amount of spin going into a reaction needs to come out at the other end.
One example is an electron and an anti-electron, known as a positron, which come together and annihilate into a photon. This is allowed because the particles going in have got a spin of a half each, and they add together to give the photon spin of 1. So the same amount of spin came out as went in, and so spin is conserved. There's a number of other conservation laws which we'll meet throughout this video. I'll just mention the 2 most fundamental conservation laws, energy and linear momentum, which, along with angular momentum, apply to everything in physics, not just particles. Actually, that's not quite true. These aren't conserved in general relativity if space-time is changing, but we don't have to worry about that for this video. So this is the first consequence of spin. The second is even more dramatic. When you get a bunch of fermions together, collectively they behave very differently to when you get bosons together in a group. When you get fermions together, they obey a rule called the Pauli exclusion principle, which says that fermions can't share the same quantum state. And this is a very good thing. The Pauli exclusion principle is what makes the electrons in atoms populate all of the energy shells. If it didn't exist, they'd all collapse into the lowest energy state, and atoms would behave very differently, because it's the outer electrons in each of the elements that sets the kind of chemical bonds those atoms can make. And chemistry creates all of the complexity in the universe.
So without the Pauli exclusion principle, every atom in the periodic table would behave almost identically to hydrogen. And so none of the complexity that makes up chemistry and biology, including us, would exist, because nothing would be solid. When we sit on a chair, it's essentially the Pauli exclusion principle that's stopping us from just sloughing through.
Bosons are different. They're allowed to share the same quantum state, and this results in some really interesting quantum phenomena like superfluidity, superconductivity, lasers, and many more. And at a more fundamental level, all of the forces we know of come from a host of virtual bosons interacting with real particles. Interestingly, it isn't just the fundamental particles that these rules apply to. The Bose statistics for bosons and the Pauli exclusion principle for fermions, they apply to collections of particles as well. So, for example, helium is known as a composite boson, as it has 2 electrons which have spin half each. If you add these spins together, you get a whole number, a boson. This means that helium atoms behave like bosons, and if you collect a load of helium atoms together and cool them down into a liquid, they will all inhabit the same quantum state and become a superfluid with zero viscosity, which means it can do weird things like flow up walls. Also, all the amazing properties of superconductors, like having zero resistance, comes from electrons coming together to form a boson called a Cooper pair, and all these Cooper pairs having the same quantum state. So fermions and bosons are more general than I previously stated. A fermion is anything with a total spin of a half integer, and a boson is anything with a total spin being a whole integer. Okay, that covers the consequences of spin. Now let's take a closer look at the spin half particles, the fermions. Now, you'll notice that the fermions are also split into the quarks and the leptons. We'll look at the quarks first. A single quark can't ever exist on its own. Quarks are always found bundled together. The up and down quarks make protons and neutrons, which make up all of the elements. But quarks can also be joined together in other configurations, like a pion, which is a particle made of a quark and an antiquark pair. Like the electrons, these quarks all carry electric charge, but they have different amounts. These ones have a charge of 2/3, and these have a charge of -1/3. These all add together to give the overall charge. For example, a proton is made up of up-up-down quarks, and so has an overall charge of a +1. But a neutron is made up of up-down-down quarks, where the charges all cancel out for an overall charge of 0. Charge is another quantity that's conserved in particle interaction, so we should add that to the list. Quarks interact with all of the fundamental forces. Let me just explain what I'm showing here. Each of these show which particles interact with each of the fundamental forces. We've got the electromagnetic force, the strong force, and the weak force. So you can see here that the quarks interact with all of these forces. Also of note, the quarks are the only particles that feel the strong force, along with the carriers of the strong force, the gluons. You'll notice I've used the word field here instead of force, and this comes from quantum field theory, which are the fundamental rules that dictate how particles interact. Quantum field theory states that there is a field associated with each of the fundamental particles, and particles are really excited states, also known as quanta of their field. So these forces are carried by specific fields, which is what we mean when we say that these bosons are force carriers. We also need to add the Higgs field, which doesn't cause a force, but these particles highlighted here get their mass from interacting with the Higgs field.
The other quarks, the charm, strange top and bottom quarks, they're just like the up and down quarks, but they've got larger masses. Also, they're unstable. In the first fraction of a second after the Big Bang, all of these decayed down into the up and down quarks via the weak force. But that doesn't mean they don't exist in the universe today. You can still find these heavier quarks in high-energy cosmic environments, things like supernovae or neutron stars, and we also create them in our particle accelerators.
Now, from the quarks, we've got a couple more conservation rules to add to the list. Baryon number and color charge. A baryon is another technical term which I'll explain. The proton and neutron are both baryons, but more generally a baryon is any particle made up of an odd number of quarks, but at least 3 quarks because quarks can't exist on their own. Baryon number is plus a third for each of the quarks and minus a third for the antiquarks. So these add together to give a plus 1 baryon number for the proton and the neutron, and is minus 1 for antiprotons and antineutrons. I haven't talked about antiparticles yet, so let's do that now. Here's a version of the standard model, but I've drawn all of the antiparticles as well as the particles. As you can see, all of the fermions have got antiparticle partners, which have got the same mass as the regular particles, but have got an opposite everything else, like charge or baryon number and other kinds of quantum numbers. We'll be meeting some more quantum numbers along the way. The next one is color charge, which we'll look at now. Color charge is a property of quarks and gluons and is an important part of the strong force interaction. Conceptually, color charge is similar to the electric charge, but instead of 2 kinds of charge, there are actually 3 kinds of color charge, which physicists have labelled red, green and blue. There's a restriction on the kinds of quarks that can join together to make a proton or neutron. The rule is that you need to have the composite particle be color neutral, which means for a proton or a neutron you need 1 quark of each color. The analogy physicists are using here is that the primary colours, red, green and blue, add together to make white, which we're calling colour neutral. In fact, you can see an example of this colour addition here if you look really closely at a pixel on your screen right now. From a distance it looks white, but if you zoom in, they're actually red, blue and green added together. But we shouldn't take this analogy too literally. Quark colour has got nothing to do with colour as we experience it through photons of light. Physicists discovered the rules of quark colour conservation, and the mixing of primary colours of light just happened to be a useful analogy that fit quite well. Antiquarks have got anti-colour, so a green and an anti-green quark can come together and make a pion particle, which has got neutral colour charge because the colours cancel out. Now there's actually an alternative analogy to the colour charge thing, which I quite like. Instead of colours, we've got arrows that always point in specific directions, as shown here. To have red colour charge means to point in this direction specifically and no other. These arrows can't be rotated. Now you can use these arrows to create valid particles. A valid combination of quarks is one where the quark arrows make a closed path. So a proton or a neutron would look like this, just an equilateral triangle. An antiproton or antineutron would look like this. And we can extend this out to other shapes, like a pion, or a particle made of 2 quarks and 2 antiquarks called a tetraquark. And what's cool is any other shape you can come up with, which makes a closed path, is also possible. This is nice because I find it a more intuitive analogy than the colour wheel, so I thought I'd tell you about it. Now, quarks can interact with each other through the strong force, and this is where the gluons come in. There are actually 8 kinds of gluons, each with a different colour-anticolour pair. And through these gluons, the different quarks interact with each other. So now, if I add the colour charges to the standard model diagram, along with all the antiparticles, we get this. This is actually all of the fundamental particles that make up the universe, which I think is important to show because there are a lot more than in the normal standard model diagrams. Okay, so that completes my description of the quarks. So now let's add some extra conservation rules to the chart. Conservation of baryon number and conservation of colour charge. Now let's move on to the other half of the fermions, the leptons. Here they all are, and here's the most famous one, the electron, which is the hardest working particle responsible for chemical bonds, electricity, atoms emitting and receiving photons of light, amongst others. Modern society is entirely built on our ability to get electrons to do what we want them to do, so they're pretty cool. The muon and tau particles are identical to the electron, just with higher masses, and they're unstable just like the heavier quarks. All the muon and tau particles that were created in the Big Bang decayed into electrons in the first fraction of a second via the weak force, which released lots of neutrinos and photons that are still flying around the universe today. New muons are also created in natural processes. One example is cosmic rays hitting the atmosphere, but any other natural process with high enough energy will produce muons and taus as well. Here are the field interaction charts again, and this time let's look at the leptons. The electron, muon and tau interact with everything except the strong force and get their masses from the Higgs field. Below them are the neutrinos, which have got very small masses and don't carry electric charge, and so these only interact with the weak force. Because of this, they're very difficult to detect as they interact with matter very, very rarely. There are three kinds of neutrino: an electron neutrino, a muon neutrino, and a tau neutrino. And these different kinds of lepton each have their own quantum number, which you can think of as electronness, muonness, and tauness. Taoishness? I don't know, I'm making these words up. In physics we actually call them different lepton flavors. These lepton flavors are another conserved quantum number. We can see this in this Feynman diagram of beta decay, where the W boson decays into an electron and an electron antineutrino. The electron has an electron number of +1, and the electron antineutrino has got an electron number of -1, because it's an antiparticle. So these two numbers cancel out to 0, which is what we started with. And so the electron-lepton number is conserved. It's important to note that the different flavours of lepton are independent. So for example, an anti-muon wouldn't cancel out an electron. This means we've got 3 more conservation rules to add to the conservation laws chart. I want to say a little bit more about the neutrinos because we still don't fully understand them. It's difficult to study neutrinos because they don't interact with matter very often. The sun is constantly spewing out neutrinos from the nuclear processes inside, and in any second we've got 400 billion neutrinos travelling through our body like it's not even there. For a long time, neutrinos were thought to be massless, but we now know that each neutrino has its own very small mass. We don't know what this mass is, and it's still being investigated, but we know that it's greater than 0, and the sum of all 3 neutrino masses must be less than 0.3 electron volts. Because they have mass, neutrinos can oscillate between the different lepton flavours. For example, electron neutrinos produced by beta decay have been observed to have a different flavour when measured in a distant detector. Another mysterious property of neutrinos is to do with their chirality, which here I'm going to be simplifying as their handedness or helicity in order to draw you a picture, which basically all means whether they're left-handed or right-handed. We've observed left-handed or right-handed versions of every other particle. But with neutrinos, we've only ever observed them to be left-handed, never right-handed. And for antineutrinos, we've only ever seen right-handed antineutrinos and not left-handed ones. Here I've actually drawn the helicity, which is how the spin aligns with linear momentum, because I don't actually know how to draw chirality. I'm only mentioning this because there's a subtle difference between chirality and helicity in any particle with mass. In massless particles, chirality and helicity end up being the same thing. But I'm really getting into the weeds here. We don't really need to worry about that for this video. The main point is we don't know why we only get left-handed neutrinos, and it breaks a couple of symmetries in physics called parity symmetry and charge symmetry.
Okay, before we get into the next bit, I'm just going to give us a bit of a break because the next bit's quite a lot to get your head around. So this is a bit of a breather. Basically, neutrinos are kind of weird. And there's still a very active area of research going on to try and study them, but they're hard to study because they don't really interact with anything. But it's interesting, there's more neutrinos in the universe than photons, so clearly they're very important. Okay, let's get back to the symmetries of physics.
Symmetry in physics is an important concept to understand. If we change some global property, like in an instant we turned the universe into a mirror image copy of itself, the question is, would the laws of physics be the same after that transformation? If so, the universe would be symmetrical with respect to mirror images, which is technically known as parity symmetry. So, is the universe actually parity symmetric? The answer is yes, except for the neutrinos. This is because a left-handed neutrino in the original universe gets turned into a right-handed neutrino in the mirror universe, but right-handed neutrinos don't exist, so the two universes aren't symmetric. For a similar reason, neutrinos also break another symmetry called charge conjugation symmetry, which is if you instantaneously turned all of the particles in the universe into their antiparticle counterparts, would the universe look and continue the same? Mostly it would, but again, not for the neutrinos. If you have a left-handed neutrino and you flipped it into an antiparticle, it would become a left-handed antineutrino, which doesn't exist. So if we go over our conservation laws again, in most cases in physics, the mirror image, or parity symmetry, does hold. It's conserved, but not by the weak force interaction that produces neutrinos, and the same goes for charge symmetry. But interestingly, if you apply both transformations, parity and charge, this combination is conserved by these weak force interactions, because both transformations get you back to a valid neutrino. So this combination, called charge parity conservation, or CP conservation, is a more general conservation law which actually applies to everything.
Except it doesn't. In the 1960s, it was found that the kaons, a specific kind of particle made up of a strange quark and an up or down antiquark, they don't obey CP conservation. And subsequently, many other examples of CP violation have been found in particle interactions. But if we also add time reversal symmetry into the mix, which is, does the universe look the same if we run time backwards compared to forwards? So we take particle interaction, then we flip parity, and then charge, and then time. This combination of transformations is conserved by all particle interactions, and this is known as CPT symmetry. Did that make sense? Maybe not. It's a lot to take in. But historically, physicists have been more and more frustrated that they need to relax these conservation laws, as it makes the overall standard model less and less elegant.
The main takeaway point from all of this is that we've got different conservation laws which are conserved by the different forces. Anything within this box is conserved by the weak force, anything in this box is conserved by the electromagnetic force, and anything in this box is conserved by the strong force. And as we're here, I'll just fill in the rest of these conservation laws. Strangeness is a quantum number attached to strange quarks, which is violated by the weak force but conserved elsewhere. And this is also true for the other flavor quantum numbers, charm, top, and bottom. I mentioned time reversal earlier, but it basically says the laws of physics look exactly the same if we flip the arrow of time and run it backwards. Interestingly, this is actually equivalent to CP symmetry, which I just talked about, and this isn't conserved by the weak force, but it is by the others. And finally, we have isospin Z component and isospin magnitude, which are quantum numbers to do with the up and down quarks. But I'll be honest, I don't understand these well enough to do a concise summary here, but I've included them for completeness, and so now at least you know that they exist. Okay, so let's do a quick review of what we've covered so far. I've described the fermions, which contain the quarks and the leptons. We've also seen all the conservation laws, as well as all the field interactions for all of the particles. These standard model interactions at the bottom are a summary of all the possible particle interactions that are allowed by the standard model, which I looked at in my previous video on Feynman diagrams, so go watch that if you'd like more details on them. I won't cover them in this video. This brings us to the last part of the standard model we need to look at, the bosons, also known as exchange particles, also known as force carriers. The gluons we've already covered when I talked about color charge and the strong force. The photons are how you are seeing right now. They carry the electromagnetic force and interact with anything with electric charge, which is all of these particles. However, the photons don't carry electric charge themselves, so they don't interact with each other, which is why I haven't included them on this chart, even though they're the carriers of the electromagnetic force.
It's a funny thought that because light is how we see things, we can't actually see light, as in we can't see it travelling past us, because we can't bounce light off it as it travels past, because light's not self-interacting. But it's kind of crazy to imagine what the universe would look like if photons did actually bounce off each other. we wouldn't be able to see anything because just the air or empty space would no longer be transparent. You just see a jumble of like random photons everywhere, and it would be a mess. So it's a good thing that photons aren't self-interacting.
The W and Z bosons are the force carriers for the weak force and have got very large masses, which they get from interacting with the Higgs field. The Z boson doesn't carry electric charge, so it only interacts with the weak force, but the W boson can have either a positive or negative electric charge, so interacts with the electromagnetic force as well as the weak force. And finally, we have the Higgs boson, which comes from the Higgs field, and particles get their masses from interacting with the Higgs field when they move through it, apart from, of course, the neutrinos. The neutrinos get their mass from some other mechanism which we haven't worked out yet, which is just one of our outstanding mysteries in particle physics. The Higgs boson itself has got mass because the Higgs field is self-interacting. And the Higgs field has got a different nature to the other fields, and so doesn't result in a force like the strong weak or electromagnetic forces. Technically, the Higgs field is a scalar field and not a vector field, like the others. Okay, so that's my summary of the standard model of particle physics. But before I go, I want to talk about gravity. When we learn physics, we learn that the four fundamental forces are electromagnetism, the strong force, the weak force, and gravity. But I haven't mentioned gravity until now. That's because we don't have a quantum description of gravity. Gravity is described by general relativity as the result of a curved spacetime. People have predicted a gravity particle called a graviton, which would be the particle associated with gravitational waves. But unfortunately, there's no way we can make a particle accelerator with high enough energies to probe this, because gravity is so weak in comparison to the other forces. Even so, physicists have been trying to squash the standard model and general relativity together for nearly a century now to try and make a theory of quantum gravity, like string theory, or a quantum theory of space-time, like loop quantum gravity. I've done a previous video on all of this if you want to find out more. Now, that's not an end to the mysteries in particle physics. Let's take a look at a few more. A big question is the issue of baryon asymmetry. According to the standard model, at the Big Bang, matter and antimatter particles were created in even amounts. But if we look at the universe today, everything we see is made of matter and not antimatter. So where did all the antimatter go? We don't know. Physicists have also made theoretical predictions of more fundamental particles beyond the standard model, stuff we haven't discovered yet. The most famous of these were the supersymmetric particles, which should have been detected by the LHC, but weren't. So currently it's not looking good for the theory of supersymmetry. Also, the most popular theory to explain dark matter is that it's made of some kind of particle we haven't detected yet, although there are many efforts to do just this. Other questions are, why are there exactly 3 generations of quarks and leptons? What are the masses of the neutrinos? What combinations of quarks are possible? And what's up with the recent results on muon precession frequency? Protons are very stable particles, but do they ever decay? Neutrons aren't stable, but what exactly is the lifetime of a neutron? Do magnetic monopoles exist? Is there a Planck particle? Why is gravity so weak? What is time? As ever, in science, more research is needed. So what does the future of particle physics look like? Historically, we've built bigger and bigger accelerators to collide particles at higher and higher energies in order to recreate the conditions billionths of a second after the Big Bang. But building new accelerators that are bigger than the ones that exist today would cost tens of billions of dollars, which might be a tough sell, so we'll have to see what happens there. But there are many experiments we can still do with the current generation of particle accelerators. And as well, we've got several large detectors without particle accelerators, which are mostly giant vats of liquid deep underground looking at high-energy neutrinos or trying to detect dark matter particles. Here's just a quick sponsor message before I round the video up. This bit's sponsored by Brilliant. It's a website and app chock full of science and mathematics content in the form of question-based courses. Watching YouTube videos is great, but to really learn something it takes practice, and one excellent option is Brilliant with its interactive questions which coach you bit by bit through a variety of courses in physics, mathematics and computer science. From the fundamentals like geometry or classical mechanics, right through to cutting-edge subjects like cryptocurrency or quantum computing, there's something for everybody. I like it because I can pick it up at any time on my phone and actually do something useful instead of just doom-scrolling Twitter again. And after a bit of phone time, I've actually learnt something, which feels great. If you're interested, you can go to my special link, brilliant.org/DOS, or you can click on the first link in the description below. And this helps me out because they know you've come from here. And on top of that, the first 200 people to sign up will get a 20% discount on the premium subscription, which unlocks all of their content. But there is a lot of content on there for free, and they're adding courses all the time, so it's worth checking out in any case.
Oh, so that's it. We've reached the end of the video. I hope it's been helpful. I'm aware that there's a huge amount of information to take in, but I've summarized it all in this image, which you can study in your own time. Like all of my posters, the digital version's free to download for your own use or educational uses, but you can buy a physical poster as well from my DFTBA store. And if you've got an inkling to buy it, this is a fantastic way to support me and my channel to help me make more videos like this. I obviously put a lot of work into them. This was a huge amount of work for this video, and I want them to be available as a free educational resource. I've also got many kind people supporting me on Patreon, which is fantastic for me to surf the very unpredictable waves of the YouTube algorithm. Okay, don't worry about subscribing unless you really want to, but do check back every so often because I've got a lot of videos lined up and you can't necessarily rely on YouTube actually showing them to you when they come out. But if you check back on my channel every couple of months or so, you should be fine. Also, if you know someone who you think might be interested in this video, share it with them. That would be cool. Otherwise, thank you for watching, and I'll see you soon.